Welcome to another video as part of the fundamentals of electrical circuits. This time we're going to try to cover transformations. Transformations are a major part of engineering, especially electrical engineering, because sometimes if we change the domain or the area that or the process we're using to solve a problem, we can solve the problem a lot easier. And this is the case here. We will take signals that are given to us in time domain, and we will move them into what we're going to call Phasor domain. And the hope is that in the Phasor domain, we will have an easier time solving the problem. Now, it's not really hope, maybe it's too weak a word to use, because this has been designed and has been created because this transformation from time domain to Phasor domain allows us to solve problems, sinusoidal steady state problems that used to be differential equations here as a more or less an algebra problem. So what we will over long haul do is we will transform, this is called the transform, we will transform our circuits to Phasor domain, solve them in Phasor domain, and this, I probably should have put this over here. We would solve it in this domain, and then when the solution is finished, we'll bring it back here. This is called inverse transform. And these transforms are kind of special features, but anyone can create a transformation domain as long as you have a one-to-one correspondent from one domain to the other domain. So you can't have a one-way street where you go one way and you can't come back. You have to be, if you want to have a valid transformation, you have to always be able to work your way back to where you started. Okay, so now let's go ahead and take a look at what is a time domain. Domain, if you remember from your early math days, domain, all it says is what is the x-axis. So in this case, the time domain, the x-axis is t, and then the vertical axis could be your voltage, current, power, whatever it is that you're measuring. For now, let's assume this is a voltage. So this might be an example of it. And let's say we have a sinusoidal signal that is drawn for us, and it maybe looks something like this. It's got a phase shift, a certain amount of phase shift here. That is theta, let's say, for the lack of, let's say theta is pi over 6. So in this case, if I write the equation for this thing, is going to be V of t is equal to, let's say, the maximum. The maximum is sitting at 10. So this is going to be 10 maximum cosine. And let's say the frequency for this one was, let's say, 2000 pi t or whatever omega. This is the omega we are putting in, and plus some angle, which in this case it looked like it's plus pi over 6 because it's shifted to the left, and that's a positive one. So how are we going to represent that in the other domain? So what we're going to do is in the other domain is most likely going to be represented as a phasor, okay, which would have some real part of V, the phasor V, and then it's going to have J. For folks who have had complex number, J is really I. In electrical engineering, we have a special use for I, so we are starting to use J as an indicator of what comes after is the imaginary part of V. And this is basically, as you remember, this is square root of -1. And the purpose it has here really is to separate the imaginary from the real part. Even in this space, we represent we use this time as the x-axis. In here, we're actually representing this as a complex number. Even though it's called a number, remember, complex number is a vector. So v, this is the vector v. Usually it's done, and because I'm bolding it because it's usually capital letters. Some books you might even see this way. Some books may put an arrow on the top of it or whatever. So what that is, when you're drawing, this is a Phasor diagram. This is referred to as a Phasor diagram, representing that value we had over there in a complex domain. So in a Phasor domain. So if you go here, we've got this complex number which tries to represent this cosine. What it does, it represented it in the real part, and this is the imaginary part. So the vertical and horizontal axis in this case are this vertical axis is the imaginary axis, and the horizontal axis is the real axis. Okay. The conversion between these two is really driven by an identity from Euler, which was a mathematician and scientist in general from earlier days. So Euler's identity basically tells us that e to the j theta is equal to cosine of theta plus j sine of theta. That's kind of the Euler's. And if you have plus and minus, those just get reflected, but theta could be plus, then you'll have a plus here, and then if theta is negative, then you're going to have a negative in here. Okay, so the identity also could be written slightly differently. It could be written as cosine of theta equals to e to the j theta plus e to the minus j theta divided. So there are different ways of writing, but these both are identity. Now let's go on and kind of see how we could take v of t over there. So in using the Euler's identity, basically says that I could potentially take this to v of t and write v of t as vm cosine of omega. This is kind of general form of writing a sinusoidal signal, or theta. That is going to be equal to vm real part of e to the j omega t plus theta. So let me go back in here. So what we're basically saying, we're using this equation and say if I take just the real part of this e to the j theta, that's just simply cosine of theta. That's all it's saying. Saying if you got a cosine of theta, that's just the real part. And since this is a constant, you can take it out of it. That's basically what they're saying. Since all the circuits we work with are linear RLC circuits, then what we can say is that the omega is constant. In other words, there is going to be one omega. Whatever your source omega is throughout your circuit is going to be the same. So it says if I want to represent this one, all I need to know, because you can rewrite this thing as Vm real part of e to the j theta e to the j omega t. So this is one value, and so there's no point for us to carry and complicated our Phasor domain. So what we're going to do, we're going to really only focus on the other portion, which is v e to the j theta. So in other words, when we take this signal v of t equal to vm cosine omega t plus phi, when we are converting it, we just gonna only keep vm, and we're gonna basically keep, because we're just gonna keep the theta portion of this thing. So and this is the real part of it. So all we need to know in order to be able to go back and reconstruct this thing is I have to know what the theta is, and I have to know what the maximum value is, and I can reconstruct it. So this is kind of the essence of how we go from time domain to a Phasor domain. Now, when we are in Phasor domain, this basically represents a complex number. As I mentioned above, the Phasor diagram is basically a complex number space where this side is real axis, this is imaginary axis, and that theta basically is the angle. V of m is how long this is, and then theta is this. Okay, and we have, so this now we can focus on this side and talk about how many different ways can we represent the same information in Phasor domain. And of course we can represent it this way. This is just saying all I have here is a maximum value and I have an angle. This is just a vertical line connected with horizontal, kind of representing angles. So this is referred to as an angular form. We already mentioned this is a Phasor diagram. So now, then can I represent any other way? Yes, you can also represent this in this form, Vm e to the j theta. You can also represent that as a V of t. And this is referred to as a polar form. One last form, and these are all equivalent to each other. They're all saying exactly the same thing. The one other way you can represent it is represent by its imaginary and real portions. So if you look at this thing, this is, and using your trig knowledge, you will see that this really is Vm times cosine of theta, and this is Vm times sine of theta. So another form you can write this is, and shouldn't have put a t in here, these are vectors. These are the vectors that represent the Phasor value of v. So another form that I can represent this is a vector value v is equal to Vm cosine of theta plus j, that indicates what comes after is the imaginary portion, Vm sine of theta. Okay, so great. So now we can take anything as long as it's in this form, I of t, v of t in that form, and write its polar equivalent. I'm sorry, the complex form or the Phasor form of it, and we can use one of these 4 forms to talk about it. Why do we have so many forms? For different purposes, there are more. One is better than the other. If you would quickly want to write the value, this is very useful. If you're trying to divide 2 entities, this is more easier to do. And if you're trying to just algebraically add and subtract, this is an easier way to do it. So let's see if we can take one of these and convert them from one form to the other. Let's say someone comes to you and say, I have got a Phasor value of I that is equal to 20 angle pi over 3, and and they ask you to, can you write the different forms of this. And first they might ask you, can you draw the phasor diagram? Sure, the phasor diagram for this is simply going to be 20, and this is going to be pi over 3. So they gave it to us in an angular form. Here is our phasor diagram, and we can do it in a polar form pretty easy. We don't even need to do anything. I is going to be equal to 20 e to the j pi over 3, and the rectangular form simply would be I equal to 20 cosine of pi over 3 minus j sine pi over 3. I don't know why I put minus plus. Okay, so now we have all the form. Now let's do this slightly differently, and let's say they come and give you a value. Say, okay, we have a signal. This time we'll say it's just for diversity. We say, okay, v is given to you, and let's say v is equal to 8.66 minus 5j. And they ask you, write this in all the forms, draw the phasor diagram, and then given omega equal to 2000 pi, write the time domain version of this. So that's easy. So for one thing is, if I want to draw the phasor diagram simply is going to be that the imaginary portion is negative, so I got a minus 5 here. The real portion is 8.66, so my vector is this. Okay, now I got to figure out what this angle is. From my trig days, I know that that angle, that whatever this angle is, theta is tangent inverse of the imaginary portion, which is minus 5. And this is arctangent, by the way. It's not 1 over tangent, it's arctangent, tangent inverse. Minus 5 over the real portion, so the front over the side tangent, so 8.66. If you plug this in, you'll find out this is equal to minus pi over 6. Okay, so using this information, I can easily write the angular form. The angular form will be, oh, one other thing. I also need to know how long this is, and simply that would be one side squared plus the other side squared. So the magnitude, this is called the magnitude of v. The magnitude of v is going to be square root of 5 squared plus 8.66 squared, and that happened to be 10. So now if I want to find out what the angular form is, just simply the length of this, 10 angle of minus pi over 6. So there is the angular form, and well, the polar form will be just simply minus j pi over 6. Now can I take this back to a time domain? Sure, time domain is basically v of t equal to the maximum, which is 10, or the magnitude, times cosine. They gave us the omega, which is 2000 pi, t, this is a pi, plus, which in this case is minus, pi over 6, which is the theta. So here is the theta, here is the omega, here is the magnitude of v. And there it is. So now what we basically went through is how do you take your signal from a time domain, go to a phasor domain and write it in phasor domain. That's all we've done. How do you go back and forth? You may want to practice this a few times to get really comfortable with it. In the next phase, we're going to use it to analyze circuit by taking the whole circuit from time domain to phasor domain, analyze it, find whatever we need to find, and then convert that information back to time domain. And if you notice, omega was constant, so we just write it in a corner and we never carry it when we are working on the on this portion of phasor. So that brings us to the end of this conversion of sinusoidal time domain source to a complex number in the phasor domain.